Assalamualaikum and hi everyone. So this video is for Chapter 4, Part 1, Operational Amplifier. After completing this video, you will be able to describe the basic operational amplifier and its characteristics. So let's start now. Operational Amplifier or OpAmp. Early OpAmp were used to perform mathematical operations such as add, subtraction, integration, and differentiations. Early units were constructed with vacuum tubes and worked with high voltage. Today, OM are linear IC that use low DC supply voltage, reliable, and inexpensive. The standard operational amplifier OM symbol is as shown in the figure. It has two input terminals. One of the input, which is the negative terminals, is called the inverting input, while the another one, which is the positive terminals, is called the non-inverting input. Operational amplifier usually has a single output. To illustrate what an OM is, let's consider its ideal characteristics. A practical OM, of course, falls short of these ideal standards, but it is much easier to understand and analyze the device from an ideal point of view. First, the ideal OM has infinite voltage gain and infinite bandwidth. Also, it has an infinite input impedance so that it does not load the driving source. Finally, it has a zero output impedance. OM characteristics are illustrated in Figure A. The input voltage Vin appears between the two input terminals, and the output voltage is AV-Vin as indicated by the internal voltage source symbol. Although integrated circuit IC OM approach parameter value that can be treated as ideal in many cases, the ideal device can never be made. Any device has limitations, and the IC OM is no exception. Peak-to-peak output voltage, for example, is usually limited to slightly less than the two supply voltage. Characteristics of a practical OM are very high voltage gain, very high input impedance, and very low output impedance. These are labeled in Figure B, practical OM representations. Another practical consideration is that there is always noise generated within the OM. Noise is an undesired signal that affects the quality of the desired signals. A typical OM is made up of three types of amplifier circuits: a differential amplifier, a voltage amplifier, and a push-pull amplifier, as shown in this slide. The differential amplifier is the input stage for the OpAmp. It provides amplification of the different voltage between the two inputs. The second stage is usually a Class A amplifier that provides additional gain. Some OpAmp may have more than one voltage amplifier stage. A push-pull Class B amplifier is typically used for the output stage. The differential amplifier is the input stage for the OpAmp. It provides amplification of the different voltage between two inputs. The slide shows the circuit for differential amplifier and the symbol of it. In the differential mode, either one signal is applied to an input with the other input grounded, or two opposite polarity signals are applied to the input. When an OpAmp is operated in single-ended differential mode, one input is grounded and a signal voltage is applied to other input. In the case where the signal voltage is applied to the inverting input, as in Part A, an inverted amplified signal voltage appears at the output. In the case where the signal is applied to the non-inverting input, a non-inverted amplified signal voltage appears at the output. In the double-ended differential mode, two opposite polarity signals are applied to the input, as shown in the slide. The amplified difference between the two inputs appears on the output. Equivalently, the double-ended differential mode can be represented by a single source connected between the two inputs, as shown in Figure B. In the common mode, two signal voltages of the same phase, frequency, and amplitude are applied to the two inputs, as shown in the figure. When equal input signals are applied to both inputs, they tend to cancel, resulting in a zero output voltage. This action is called common mode rejection. Its importance lies in the situation where an input signal appears commonly on both OpAmp inputs. Common mode rejection means that this unwanted signal will not appear on the output and distort the desired signals. Desired signal can appear on only one input and with opposite polarities on both input lines. These desired signals are amplified and appear on the output. Unwanted signals or noise appearing with the same polarity on both input lines are essentially cancelled by the OpAmp and do not appear on the output. The ability of an amplifier to amplify differential signals and reject common mode signals is called the common mode rejection ratio, CMRR. CMRR can be defined as CMRR equal to AOL over ACM, where AOL is the open loop differential gain and ACM is the common mode gain. CMRR can also be expressed in decibels as CMRR equal to 20 log AOL over ACM. The open loop voltage gain AOL of an OpAmp is the internal voltage gain of the device and represent the ratio of output voltage to input voltage where there are no external component. The open loop voltage gain AOL is set entirely by the internal design. Open loop voltage gain can range up to 200,000 or 106 decibel and is not a well-controlled parameter. For example, if a CMRR of 100,000 means that the desired input signals differentials is amplified 100,000 times more than the unwanted noise or common mode. Okay guys, one quick examples. What is CMRR in decibel for a typical 741C OpAmp? The typical or open loop differential gain is 200,000 and the typical common mode gain is 6.3. Therefore, CMRR is equal to 20 log AOL over ACM. So 20 logs 200,000 over 6.3. Therefore, in decibel, CMRR for 741C OpAmp is equal to 90 dB. Input offset voltage. The ideal OpAmp produces 0 volt out for 0 volt in. However, in practical, a small DC voltage appears at the output when no differential input voltage is applied. This is caused by the base emitter voltage of the differential amplifier input stage of an OpAmp. The input offset voltage VOS is the differential DC voltage required between the input to force the output to 0 volt. Typical value of input offset voltage are in the range of 2 mV or less, and in the ideal case, it is 0 volt. Input bias current. The input bias current is the DC current required by the input of the amplifier to properly operate the first stage. By definitions, the input bias current is the average of both input current I1, I2, and is calculated as follows. I bias equal to I1 plus I2 over 2. The concept of input bias current is illustrated in figure as shown in the slide. Input impedance. Two basic ways of specify the input impedance of an OpAmp are the differential input impedance and the common input impedance. The differential input impedance is the total resistance between the inverting and non-inverting input as illustrated in figure A. Differential impedance is measured by determining the change in bias current for a given change in differential input voltage. The common mode input impedance is the resistance between each input and ground. And is measured by determining the change in bias current for a given change in common mode input voltage. Input offset current. Ideally, the two input bias current are equals and their difference is 0. However, in practicals, the bias current are not exactly equals. The input offset current, IOS, is the difference of the input bias currents. Actual magnitude of offset currents are usually at least an order of magnitude 10 times less than the bias current. In many applications, the offset current can be ignored. Output impedance. The output impedance is the resistance viewed from the output terminals of OpAmp, as indicated in the figure. Slew rate. The maximum rate of change of the output voltage in response to an step input voltage is the slew rate of an OpAmp. The slew rate is dependent upon the high frequency response of the amplifier stage within the OpAmp. The slew rate is expressed as delta V out over delta T. A pulse is applied to the input and the resulting ideal output voltage is indicated in figure 11b. The width of the input pulse must be sufficient to allow the output to slow from its lower limits to its upper limits. A certain time interval, delta t, is required for the output voltage to go from its lower limit negative max to its upper limit positive Vmax. Once the input stage applied, the slew rate is expressed as slew rate equal to delta V out over delta T, where delta V out is equal to positive Vmax minus Vmax, and the unit of slew rate is volt per microsecond.